Welcome to the product overview for IMIME. IMIME is a robust mesh generation software package that is designed to efficiently produce meshes for a wide variety of applications. This video provides an overview of the IMIME software package, its user interface, and its capabilities. The typical computer-aided engineering, or CAE process, begins with a 3D CAD model representing the volume that forms the basis of a simulation. This three-dimensional model must be subdivided into small volumes known as cells or elements. This process of subdividing the 3D model is known as meshing and can be difficult, non-intuitive, and time-consuming. But we believe it doesn't have to be. IMIME was created to get from CAD to your solver, such as CFD++ or a variety of other available solvers, quickly, efficiently, and intuitively. IMIME provides high-quality meshes without high levels of difficulty. It provides an intuitive meshing process with a very short learning curve. In fact, you'll be building meshes in minutes. IMIME provides meshes that complement the strengths of Metacomp solvers. And IMIME provides automation capabilities that maximize your productivity. IMIME provides the same intuitive and guided process to generate both 3D and 2D unstructured meshes, including structured boundary layers. IMIME meshes can be used for all Metacomp applications. In fact, the vast majority of Metacomp validation cases and published studies have utilized meshes created with IMIME. To illustrate the intuitive nature of IMIME, let us first examine the basic workflow of creating a mesh. IMIME uses a geometry-based meshing process. As such, the first step will be to load the CAD geometry. Users then have access to all of the CAD entities, such as vertices, edges, and faces. The CAD entities form the basis of the IMIME mesh, ensuring that the results represent the domain of interest as accurately as possible. IMIME accepts numerous native and discrete model formats, including industry standards such as Parasolid, ACES, and STL. After loading the geometry, the CAD entities are grouped into families. This is done for multiple purposes. One reason is to group all of the CAD entities into families for the purposes of mesh control. Many of the features that we'll discuss later in this presentation are activated on a per-family basis. Another reason for grouping CAD entities into families is for boundary conditions. Each of the families defined in IMIME will become available to the user in the solver for the use of defining boundary conditions. And finally, users may wish to group CAD entities into families for the purposes of post-processing. For example, users may wish to measure forces and moments on regions of the geometry. Those regions can be grouped into families, which will become available as boundary conditions and available for post-processing purposes. After grouping into families, the users will specify the mesh sizes. This is done on a per-family basis, but can also be done with a variety of density regions, such as boxes, cylinders, spheres, and frustums. After setting mesh sizes, the user then generates a surface mesh. This provides a convenient mechanism to verify the mesh size controls. Users can go back and make adjustments as necessary. If the user is satisfied with the surface mesh, then structured layers can be defined on a per-family basis. Finally, the volume mesh is generated. If the volume mesh is deemed acceptable after inspection, it can be exported and will become available for the solver. The IMIME user interface is designed to guide the user through the meshing process in an efficient and an intuitive way. The next portion of the presentation shows the features of the user interface that make IMIME both intuitive and robust. IMIME, which stands for Integral MIME, uses the Advanced User Interface. The Advanced User Interface is built upon the Integral Computational Multiphysics, or ICMP, concept and infrastructure. This infrastructure provides a common interface across all products in the Integral series. This interface allows IMIME to have an intuitive and simple guided meshing process, and allows for the inclusion of advanced automation capabilities to increase the user's productivity. A key aspect to the IMIME Advanced User Interface is the action tree. The action tree consists of individual action items, and each action item has associated with it an action panel. Users progress through each action item in the action tree. The action tree guides the meshing process. However, it does allow users to move up and down, and a thinking engine adapts the action tree items based upon the selections made. This ensures that users never miss a step in the process. Let's look at an example. The image on the left-hand side shows an initial mesh. A user may determine that additional refinement is needed on the nose cone, shown within the red box. There are many ways to accomplish this refinement. In this case, the user decides to go back and define a density region. They simply navigate back, click on the density region action item. The corresponding action panel will open. The user answers some simple questions to define the density region, and then clicks OK to define the density region specifications. The thinking engine then analyzes the changes made in the density region panel and automatically takes the user to the next action item that needs to be addressed, in this case, the surface meshing options. This ensures that the users never miss a step. The advanced user interface also includes many other intuitive controls. For example, when creating families, there are easy mouse controls allowing users to simply point and click on the CAD entities that will be used to define the families. In addition, selection boxes are available, allowing users to select multiple items simultaneously for inclusion into families. Density region controls are drawn on screen. Density regions can be manually adjusted by entering the coordinates that define the density region, or can be adjusted dynamically using on-screen controls. Structured boundary layers are applied on a per-family basis. Users simply need to define some basic settings of the boundary layer and simply check off a box next to the families from which those boundary layers will be generated. The next part of the presentation shows some of the advanced capabilities that can be enabled through IMIME's guided meshing process. The IMIME interface is flexible and provides intuitive access to a wide range of advanced capabilities. IMIME allows for quadrilateral surface meshing capabilities. In this example, the surface shown in red has been meshed with quadrilateral elements, which are then extruded to form hexahedral prism or boundary layers. IMIME has the capability to produce hexahedral elements in the volume core of the mesh. IMIME can do point-based refinement, which provides a very flexible capability to do refinements of shock waves or other complex physics that occur away from boundary surfaces. IMIME has growth rate controls, which are available for both surface and volume meshing, allowing for a smoother transition between refined regions and coarse regions. IMIME has discrete model meshing capabilities, which can form a very powerful tool in addressing CAD model issues that can result in sliver elements. IMIME has curvature-based refinement capabilities, which can be applied on a per-family basis. This will automatically refine surfaces based upon curvature in the native geometry. IMIME has extrusion meshing capabilities, which can create a semi-structured mesh for pipe configurations, thus reducing the overall mesh count and improving mesh quality. IMIME has mesh matching capabilities, which can define matching surface meshes. This capability is useful for periodic geometries. IMIME provides the capability to specify the location of mesh vertices. This can be useful for post-processing applications. IMIME also includes intelligence. Wizards are included, which can streamline the meshing process. IMIME currently includes problem-based wizards, such as the external aero and automotive wizards, and now includes a general size automation wizard. The AUI also allows for the rapid generation of customer-driven wizards to satisfy compact classes of problems. Here's an example of a problem-based wizard. On the left-hand side, we see the Aerodynamics wizard. Users simply answer a series of simple questions about the problem they're trying to solve. For example, the user enters the free stream Mach number, the altitude, and temperature, and from that, the wizard determines density region refinement, prism layer settings, and automatically defines an initial setup for CFD++. The general size automation wizard automates the refinement of geometric entities for general classes of geometries. The refinement is based on the size and complexity of the model and can be applied to both native and discrete models. Users simply choose the level of refinement from options such as very coarse through very fine, along with some simple controls for limiting of mesh size on thin surfaces. The general size automation wizard also streamlines the setup by minimizing the number of families that a user needs to generate. For example, the need to specify families for mesh controls are minimized, and in fact, the user can place all of the geometry associated with a given boundary condition into one family and let the wizard take care of the rest. Here are some examples showcasing the capabilities of the general size automation wizard. This case shows an appended ship hull where the entire geometry is placed into a single family, allowing the automation wizard to select all sizes necessary. Here's an example of an appended submarine, also showing the capability of placing all geometry into a single family and allowing the automation to determine the sizes automatically. IMIME also includes STL Automation. Many complex CAD geometries are exported in STL formats. For example, here's a 3D car. This car consists of millions of individual STL facets. These facets are grouped into dozens of individual boundaries. Manually grouping these into families can take hours. However, the STL automation can automatically group the different boundaries into families, saving hours of work. IMIME also provides the ability to define analytic geometries using a series of 2D points. These 2D points can be used to generate 2D discrete models, which can then be extruded into 3D models. This type of automation is ideal for large eddy simulation type computations. We have seen how IMIME provides an intuitive and guided meshing process. Now we will show several examples of meshes that IMIME has produced. This first example illustrates the use of IMIME in predicting golf ball aerodynamics. The model consisted of a detailed golf ball, including the divots. A 3D unstructured grid was generated with structured boundary layers, utilizing nested density regions. The next example showcases a launch complex flame deflector. This example utilized a wide array of complex physics that needed to be resolved with the grid. The starting geometry was provided in STL format. A series of box refinements were used along with prism layers on the trench surfaces and nozzle interiors. IMIME has been used to build meshes for high-speed land vehicle applications. These applications addressed a variety of speeds along with propulsion exhaust and slip angles, requiring the resolution of local transonic effects. Nested refinement boxes were used to resolve the important physics, and several IMIME capabilities were used to efficiently address geometry changes for design studies. IMIME has been used for external aerodynamics applications, including transonic flow with angle of attack. Exceptional results have been achieved at all levels of refinement using IMIME grids. IMIME has been used for icing model studies of complex ice shapes with simulations that include mesh morphing. IMIME has also been used for turbomachinery applications, where localized curvature-based refinement can be utilized to minimize user time in specifying meshes. More examples, such as these, can be found on the Metacomp Technologies website. To summarize, if you want high-quality meshes without high levels of difficulty, if you want an intuitive meshing process with a very short learning curve, if you want meshes that complement the strengths of Metacomp solvers, and if you want maximum productivity through automation, then you need IMIME. For more information about IMIME, you can send an email to info@metacomptech.com. Thanks for your attention, and we hope to hear from you soon.